Hey everybody, happy Thursday to you. Um, Hopefully you've had a chance to go through the practice test that was posted. That reminder is one teacher's guess as to what it might look like. Now that I've actually gone through it, I can tell you that there were definitely some difficult parts to this, and because the writers of the test know that you're going to have your notes available to you, that um, you'll you'll have a calculator sitting next to you, even when a calculator is not required for the problems. I wonder if that's going to affect the level of difficulty. I wish I could tell you what the answer is, but I thought this one, if anything, seemed a little bit on the more difficult side of what I thought. Usually, you'd have some more uh, give me questions that are a little bit more of a toss up. I don't know if easy AP calculus questions is a contradiction in terms, but there wasn't a lot of sigh of relief on this one. There was a lot of stuff. And so, in order to hopefully get this done fairly quickly and not spend too much time, I have my work all written out. I'll just guide you through it, and you'll have to maybe pause every once in a while and go back and look at stuff. But the information we're given on question number one is a graph and a table. We can assume from the graph as given that this graph of f is crossing the axis at -2 and +6. I can't see my scale on this right now, but on the actual test, you were able to see that this tangent line, by counting grid markers and stuff like that, you were able to determine that the slope of this tangent line was equal to 2. It went over 1, up 2, over 1, up 2. And then we are also given some information about some derivatives of f. And then we are told, let's see, right away on part A, here's this key phrase: g is the integral of f of 2t. And so we're going to use that eventually to say that if g is the integral of f, then f is the derivative of g. But of course, that 2t is going to introduce some chain rule stuff along with it. But let's go ahead and start making our way through this one. Question number one, we want a fourth degree Taylor polynomial, which means we need the value of f, f prime, double, triple, and quadruple prime. And so I just started figuring out what these things were. We're given this information. G is the integral of f of 2t from 3 to x. So plug in 3, and that is the infinitesimal integral. So it's definitely 0. G prime, here's fundamental theorem of calculus. The derivative of g is the derivative of the integral of f. And so that's it. That's just fundamental theorem of calculus there, giving us that much. And so we can plug 3 into that. And so f of 2 times 3 is f of 6, and we just look at the graph and determine that that is 0. And then we're just taking derivatives. Here's the chain rule stuff that comes along with it. The derivative of g is g double prime. The derivative of f is f prime of 2x times the derivative of 2x. So there's the extra 2 that ends up tagging along, and every time we take a derivative, that times 2 times 2 times 2 pattern will follow. And then let's see, f prime of 6 we determined by looking at the graph. F double prime and f triple prime were both given in the table. And so that gives us all of our values. And so we plug them into the Taylor series. Oh, looks like I goofed up. This should be, oh, nope, I take it back, take it back. This was 3 factorial, 12 over 3 factorial, 12 over 6 reduced to 2, and then 16 over 24 I reduced to 2/3. You do not need to do that, but I did. Part B, find the coordinates of critical points of G. Well, the critical points of G are going to happen when its derivative is equal to 0, and its derivative is f. There's our fundamental theorem of calculus again. So we stated this already in part A. We don't have to restate why this is, but I thought it would be useful to write it out. And then because I'm looking for the places where f is equal to 0, I'm going to keep in mind that what we're looking at here is f of 2x. And so if 2x is equal to 6, then this is really happening for the g function at x equals 3. And then similarly, if we're looking at f of 2x, then the value of x we're looking at is -1 because that's what gives a value of -2 because that's where the graph is crossing the axis. And then I just stated simply that at x equals -2, that's where f is changing from positive to negative. And so making this 2-to-1 switch between f and g, g has a maximum at x equals -1 because it's changing from positive to negative. Excuse me, f is changing from positive to negative. And then similar logic to find the minimum at x equals 3. Part C, this was annoying to me. This seems like a much higher degree integration by parts than what I would expect for you guys to see on the actual thing on May 12th. So I'll just take you through this. It's a double integration by parts. I don't see any other way of doing this one. So that's what I did. First step, u is x squared, dv is everything else. And so the antiderivative of the fourth derivative is the third derivative. And everything else is pretty standard there. And then I just went ahead and did it right away because I saw we're making progress here. So I went ahead. I suppose you could factor that 2 out of there. I just left it in because it wasn't a nasty derivative. And here again, the antiderivative of the third derivative is the second derivative. And so by that point, we get down to this as our integral. And we can do that. We can pull the 2 outside and take the antiderivative of the second derivative. And I didn't really deal with the 1.5 and the 3. At the end of this, everything's being evaluated from 1.5 to 3. I suppose you could be doing some of that as you were going. I chose not to. And I just waited until the very end to start plugging in values. So plug in 3, plug in 1.5, and subtract. All these values that are plugging in are coming from different places. F double prime came from the table. F prime came from the graph. F of 6, I guess that's from the graph as well. F double prime, that came from the table. This one was just given to you, f prime of 3, somewhere in the statement of the problem. They said, given that f prime of 3 is equal to -1/2, evaluate this. So that's where that came in. And then finally, f of 3, we found that from the graph. So the derivative at 6, again, that was looking at the grid lines and counting over 1 and up to. And then plugging all these values, I got an answer of 47. Moving along to part D, this is a geometric series. Does it converge or diverge? And when I saw the factorial there, that just was an indication to me that we should probably do this as a ratio test, plus the fact that it's geometric and I know stuff about the ratio of terms in a geometric series. So I went ahead and plugged it through the ratio test. The factorial part, that cancels out like it always does, and we're looking at the ratio of the next term to the previous term. And we were given that this was a geometric series. And so I've got a ratio. This ratio is bigger than 1, but I don't really care about that because whatever this number is, even if it's 1,000, eventually this is going to 0. And so whatever this ratio is, it's going to be multiplied by something that's going to 0. And so this product ends up being 0, which is less than 1, which means it is convergent. And then finally, part E. When I first saw this, I saw what was happening here, and I instantly thought about E. Nice thing to recognize. The limit as n goes to infinity of this is E, and that feels like too much of a coincidence to just show up. So interesting. I didn't even notice. This is part E, so subconscious hint maybe. But first, the first part of the, what is this? The sixth part of this problem. Yikes. Find the third partial sum. I just wrote out the terms. They gave us the first one and then told us how to define the subsequent terms. So the first one is 1. I plugged 1 into this and got 2, and then I plugged 2 into this and got 9/2. And so the third partial sum is the sum of the first 3 terms, 7.5, 15/2, however you would like to express that. Maybe that's our sigh of relief. That part of that problem wasn't all that bad. And then ratio test. They tell us to just use the ratio test. I guess the trick on this one is to recognize that this is the next term and this is the previous term. And so if I put it in terms of b sub n, this is the next term, this is the previous term, and that b sub n just cancels out, and we're left with just the limit as n goes to infinity of that stuff that's on the top, which again, that is e, which is bigger than 1, 2 point something. So we really need to know about the value of e. A really nice thing to recognize, it certainly doesn't happen every year. It probably won't happen this year, but it happened on this practice test, and it came in handy to know that that was the value of e. So there we go. I don't know how many points we can think that we've accumulated so far, but um, a lot of really tricky parts, a lot of kind of painstaking parts, especially in parts A and I believe it was A and C specifically. Where was that? Part A, yeah, part C was kind of annoying. But moving on to the second question. As soon as I saw this question, I thought about logistic. First, because of the slope field where you can imagine a solution to this thing. And then also the differential form that we're given. This has the logistic feel to it. It is a logistic, but then they never really did a whole lot with that. And also, I don't really like this. I think on an AP test, they would tell you that there is an equilibrium solution at y equals 10. Here, we're just going to have to assume it from the graph that this is actually happening at a 10 and not 10.2 or something like that. I think if this was an actual AP test, they would be more explicit about stating that. But in any case, we're going to use that information to say that, well, since that is where the equilibrium solution, that must be my carrying capacity, which I can plug in for that value. Let's see, aside from that, I guess f of 0 equals 1, that's a pretty significant thing that we'll have to keep in mind, especially as we go on to part A, which is Euler's method. I taught you guys how to do this using a table. You don't have to use a table, but I think it's the nicest and most concise way to keep the information all organized. Here's the point where we're starting. The derivative is defined by the differential equation, which you had to plug in this value for m in order to do this. But then they wanted it in terms of k. So in terms of k, it's 9k. And then because we're taking 2 steps covering an interval of size 2, each one of the steps is 1. So these 2 columns turn out to be the same in this case. And then that's how much the y value changes by. So 1 plus the delta y, 9k. And then repeat the process, plug it in. I've got k times y is 1 plus 9k, 10 minus y is 1 plus 9k. And then really, in terms of the answer to this question, we probably could have just said 1 plus 9k plus this whole nasty expression. I chose to multiply it out and FOIL it and get it into simplest polynomial form, but that would not be required. This would be okay, or even a less simplified version of that. This seems messy. This seems like a little bit more painstaking than I would expect to see, but we'll see. You'll see. I don't even know if I'll get to see this one. Anyway, part B, find f double prime. And at first, when I started this problem, I thought about the second derivative, and I wasn't sure what to do, and then I was reminded of this. We're given the first derivative in factored form. I multiplied it out so I didn't have to deal with the product rule. The derivative of this looks like that. Don't forget about your chain rule. The derivative of y in terms of x is dy dx. I called it y prime here. And then the rest of it's just simplification. Y prime is dy dx, so I'm plugging that in place. We're given that y of 0 is 1, so once we get done simplifying, I could have done it here. I could have plugged in the value of 1 way back there, or I could have plugged it in anywhere that I saw a y. I guess I didn't figure that out until I got to this point, and I had this nasty stuff. Here again, I think this is a fault in the teacher's writing of this question. I don't think they wanted it in terms of y. I suppose if they wanted in terms of k and y, then this would have been the answer back here. But I mean, we know what the value of y was, so I plugged it in. And once everything's simplified, I got 72k squared. Part C, the actual value is 4.6, and they want to know if our answer is an overestimate or an underestimate. I said because At first I was going to refer to maybe to the shape of a logistic solution, but instead I just said that it is concave up for all the values between 0 and 5, which I suppose I'm using what I know about logistic equations. Because the carrying capacity is 10, I know that between 0 and 5 it's going to be increasing at an increasing rate, and so that's concave up. Um, and so because the value that we have, the 4.6, is less than 5, I know that the graph is going to be concave up on this entire interval, which means if I have a graph that is concave up, our Euler's method approximation, a first degree approximation, will give us an underestimate. And this, you don't have to say this. If you have a graph that's concave up, a linear approximation will be underneath the curve, and that's enough sufficient justification. And then finally, part D, they managed to get L'Hopital on this practice test. Let's see, the limit as x goes to infinity of g of x minus 10 over f of x minus 10. Well, because of the shape of, or the feel of our slope field here, solutions above the carrying capacity will end up approaching the carrying capacity. As long as we don't have a negative y value, everything's approaching 10, which means that both of these parts, this is approaching 0, this is approaching 0, because both f and g are approaching 10. And so since both the numerator and denominator are approaching 0, L'Hopital applies. So I applied it. And when I did that, we just had g prime over f prime. And because these are solutions, g is the particular solution, f was a particular solution that we were told before, because these are both solutions to the differential equation, their derivative is the dy dx that we were given. And of course, since those are both the same, the ratio of those two is 1. And so the limit is 1. So there we go. As I mentioned, I think we should maybe take a step back at this point and go back farther. There were a lot of people who asked about more basic stuff than the contents of this test, so I think we'll probably do something fairly similar. I suppose you've got a long weekend because the governor says we shouldn't have school on Friday or Monday, so I might I'll get this one posted by the time you're watching this video on Thursday. The AB equivalent, I've got a few of them that I found. I'll probably just, well, maybe I'll post all 3 of them, but I'll tell you which one I'll be analyzing. So those of you who have a lot of time this weekend and want to get a lot of practice will have that opportunity. So work on that this weekend, have that ready to go on Tuesday, and I'll have a similar video to this ready for you to watch on Tuesday. Unless, of course, I get feedback that says that this was not useful and we should be doing something else. I'm open to suggestions. I certainly do plan on doing some solids of revolution before we're done with this. I don't think we've seen nearly enough of that. But aside from that, I'll wait to hear from you. Otherwise, I'll plan with the plan that I just described. Good luck to you all, and we'll see you next time. Bye-bye.